Lasers come in all shapes and sizes. Nevertheless, in order to control your laser, you need to measure it. Because, as Deming said, if you cannot measure it, you cannot control it. The purpose of this video is to show you how to use the Ophir Spiricon M2 200 to measure almost any laser, whether it's fiber delivered, direct delivered, or articulated optics. Using an M2 system as a beam diagnostic tool can increase your profitability by reducing waste and giving you better consistency. Making an M2 measurement with an Ophir Spiricon M2 200 is quite simple because it is a completely integrated system consisting of a high-resolution camera, a USB interface that connects to the computer, and a removable filter wheel assembly behind which the focusing lens is placed. Using a high-resolution camera with 4.4 micron pixels allows the system to measure spot sizes as small as 70.1 microns, which is excellent for extremely high brightness lasers. A unique aspect of the Ophir Spiricon M2 system is the fact that the focusing lenses are interchangeable, allowing the user to change wavelengths at will without disassembling the system. Once the lens is inserted, the filter wheel system swivels back into position for operation. Most lasers will provide much too much energy to the system, and for that reason a sampling optic system needs to be set up, consisting of some sort of beam attenuator, as you see here, which attenuates the beam and sends that beam to a pair of turning mirrors, which then allows the user to adjust the beam so that it enters the M2 system perfectly parallel to the mirror system inside. When setting up the system, the advantage of using the removable filter wheel accessory allows the user to take that accessory out of the way, remove the focusing lens, and then perform the adjustment using the camera to make sure that the beam is parallel. Once the alignment has been completed in rough form, the focusing lens can then be reinserted and fine adjustment can be made. This shortens the amount of time when doing an M2 measurement for the first time. One of the simplest ways of aligning the beam is by using nothing more than a steel rule and noticing where the beam falls. Once you know where the beam is on the first mirror, that mirror indicates where the beam should fall on the center of the M2, as you see here. Once that's completed, then the horizontal alignment can be made. The software here consists of three major screens. The right-hand screen shows the actual beam size versus distance curve. The lower left-hand side shows each individual beam, and the upper left-hand side shows you all your calculations. It is all three that allow you to make these measurements automatically. Now that the M2 is aligned to the laser, all we have to do is set up the parameters for the run. We open up the dialog box, define the laser, the wavelength, the length of the focal length of the lens, and the distance between the laser and the M2. We also pick the beginning and ending point of the run, and also the increment in millimeters. From this point forward, the system operates completely automatically. As it is known, when you transition from the near field to the focus and back into the far field, the intensity of the beam will change. This will exceed the dynamic range of the camera. which is where the automatic filter wheel system comes in. The computer software actually picks the proper filter combination so that the camera is in its most linear range and measures each individual beam width at that point. In between points, it performs the patented UltraCal, which then resets the baseline in accordance with the ISO 11146 specification. As soon as 5 data points have been accumulated, the algorithm in the computer will predict the remaining curve and then readjust itself as each additional point is captured. This happens completely automatically. As you can see, the information presented in the calculation box shows you the m-squared in both x and y, the divergence in x and y, the location of the waist in x and y, and a number of other important parameters like Rayleigh range. As we approach the area of the waist, where the beam is the smallest, the ISO specification requires that the increment distance be divided by 1/2. That is, if your increment is 10 millimeters throughout the run, at the waist the increment will now be taken in 5 millimeter distance increments so that more points can be gathered around the waist. Because an error at the waist can cause a large error in the m-squared calculation. Since the m-squared calculation itself is one equation but 2 unknowns, what we are actually doing is preparing a curve based on the empirical data and then deriving the parameters from that curve so that the equation itself can be solved. When measuring around the waist, in this particular case with a short focal length lens, the beam size might be as small as only 100 microns. It is for this reason that we have chosen to use a camera with 4.4 micron pixel pitch so that the accuracy of the small spots is maintained. As we pass through the waist, the increment then increases once again, and the information is continued until we complete the run. A normal run will take less than 5 minutes. Each individual point has already been saved along with the actual beam width measurement and the raw data. As you can see, in the next scene, we will show you what the beam looks like at that particular point. And there's the point. And there is the corresponding beam at that point. Okay, so we've done a measurement. Now let's see how we can adjust that measurement to make it look more accurate. You'll notice the international no symbol in the screen, and that's used for determining whether or not a point or series of points in your run are valid or not, because those points can be manually cut out of the calculation to determine whether or not the m-squared calculation is still valid. All we do is we use the icon, which will then produce a way of removing that data point, and then we can inspect the resulting calculation live to determine whether or not the calculation has changed. In addition, you'll notice that each and every point will also show a corresponding image of the beam. This beam can also be enlarged. Here's the image of that same beam at the focus, which was only 100 microns, enlarged approximately 9 times using the software Zoom. You can see on the right hand side where the arrow is, the little square shows what you're actually looking at as far as portion of the entire camera. The M² 200 is a universally useful industrial and laboratory tool. This concludes this demonstration. We hope you enjoy it.